So this left a mystery. If there was a negative subatomic particle called the electron, that means that there was a positive component to the atomic structure as well. And so this began the discovery of the atomic nucleus, and work on the atomic nucleus began in 1909, and it emerged from the fact that Thomson's discovery of the electron was irrefutable. Experiment after experiment verified what Thomson had discovered. Millikan's work demonstrated that the electron was a tiny fraction of the mass of the atom, so this was a major scientific mystery. That is, what was the structure of the atom? The rest of this atom had to contain a net positive charge to balance the electron charge, but it also had to contain an overwhelming fraction of the total mass of the atom. So what was the architecture of the atom? That was the mystery that was central to scientific thinking in the first decade of the 20th century. So the first answer to this question was a new model of the atom. And this new model of the atom was put forward by none other than J.J. Thomson, who had discovered the electron. And this is a very famous model, and it was termed the plum pudding model. And the plum pudding model can be diagrammed very easily. It was a sphere of the size of the atom that had an intrinsic positive charge to it. It was a continuum of positive charge articulated occasionally by a negative electron that existed within that sphere of positive charge. So that was the plum pudding model. And that model, again, was believed to be true by J.J. Thomson. But then another very important scientist arrived on the scene. And that scientist was Ernest Rutherford. And he was a young New Zealander who arrived in England in the very early part of the 20th century. And he was a strong proponent of the plum pudding model. And he worked for J.J. Thomson. And it wasn't surprising that he was a strong believer in the plum pudding model since he was working for J.J. Thomson. But Rutherford's brilliant breakthrough was to use an important new discovery. And that new discovery was of radioactivity. And that discovery provided him with the experimental tool that he needed. It was Henry Becquerel and Marie Curie who discovered radioactivity, and they had identified 3 specific particles. They had identified from radioactive decay alpha particles. Alpha particles were helium nuclei, and these helium nuclei, these alpha particles, were emitted at very high velocity during radioactive decay. The second particle were beta particles, and they were electrons also emitted from radioactive decay. And finally, gamma rays, which were electromagnetic radiation, and they too were emitted simultaneously with alpha and beta particles during radioactive decay. Well, it was the genius of Rutherford to create an extremely simple experiment, and he realized that alpha particles had the attributes that he needed because they were massive, being the nuclei of helium atoms. They were massive relative to an electron, that is, and they emerged at very high velocity. So Rutherford built an experimental apparatus that is disarmingly simple, but is extremely powerful, and it turned out to be exactly what was needed to dissect the structure of the atom. So let's take a look at what that apparatus consisted of. The apparatus consisted of a radioactive source centered in the lead block with a tiny hole in it, and that lead enclosure allowed alpha particles to emerge in only one direction in a very narrow beam. Then he set up a target of gold, a very thin target, just a few molecules thick, and that gold foil sat in the beam of alpha particles coming out of the source. And then he set up a detector, and this detector was circumferential, and that meant that it could detect alpha particles in any angle coming away from the incident direction. that meant that every time an alpha particle hit this detector, it set off a tiny point of light. And so he could then monitor exactly what the angular pattern of scattering of those alpha particles from this gold foil was. And so that was the experiment that he set up. Very simple, very direct, but let's see what happened. And this goes down as one of the most remarkable stories, because in the opening phases of the experiment, that was in 1909, Rutherford and, by the way, J.J. Thomson thought that they'd confirmed the plum pudding model. And the reason they thought they'd confirmed the plum pudding model was that virtually all of those alpha particles emitted from the source that struck the gold foil moved straight through the gold foil and struck the detector without any deviation in its trajectory. So virtually all those detected alpha particles displayed little or no change in their trajectory. So initially there was great celebration. They had proved by direct experiment that the plum pudding model was correct, because that sphere of positive charge that was part of that model, articulated by a few electrons, clearly was experimentally verified by the fact that those alpha particles just flew right through that sphere of positive charge without deflection. But then things started to change. As the data set evolved, something remarkable happened. And what was unbelievable was that every once in a while, a little flash of light occurred on that detector, which meant that the alpha particle had struck the gold foil and bounced in a backward direction. But it was only one particle in 20,000 that showed this back trajectory. But tens of thousands of alpha particles are emitted by these sources. So within 2, 3, 4 weeks, all of a sudden it became clear that in fact a very tiny fraction, but a consistent fraction, of those alpha particles were backscattered from that gold foil, striking the detector in a decidedly different trajectory from the initial emission of the alpha particle from the source.